Okay, so this mini lecture is on rapidly varied flow, and specifically one aspect of rapidly varied flow, which is hydraulic jumps. Now, there's other instances of rapidly varied flow that we're not going to talk very much about, but rapidly varied flow is occurs when the water flow depth changes abruptly over very short distances. And so this is in contrast to gradually varied flow, which we'll cover next, in which the channel depth changes sort of slowly with distance, and we can predict what that surface profile is going to look like in detail. In the case of rapidly varied flow, we can't. We can predict what happens before and what happens after. We can predict certain aspects of it, but not exactly what the water surface is going to look like. So we're going to be talking about hydraulic jumps, but you can also have channel transitions in which you go from subcritical flow upstream to supercritical downstream, like in a channel narrowing. If that happens over a very short distance, you can have rapidly varied flow. Flow over spillways, sort of waterfalls or things like that, flow in channel junctions, flow through trash racks or screens, flow between narrowly spaced bridge piers, things like that. So hydraulic jump occurs when we have a rapid change in flow depth from a small depth to a large depth, and basically happens when we go from supercritical flow and supercritical velocity and we hit a subcritical region. The water's forced to slow down and transition to subcritical flow. So there's a couple cases where this can occur. It'll naturally occur when the depth at any point is less than the critical depth, i.e. we are currently in supercritical flow, which is less than the normal depth. Right? If the normal depth is in the subcritical flow region and we are currently in the supercritical flow region, then over time the flow is going to want to get back towards its normal depth, and so it's going to have a hydraulic jump to get back to that subcritical flow region. Of course, it can also happen in cases where sometimes the normal depth for a channel is actually in the supercritical flow region, but we have some sort of control in the channel that's going to temporarily force it to subcritical flow, like behind a sluice gate or something like that. But often we will look at this condition to see if a hydraulic jump is going to form. Now, the depths on either side of a hydraulic jump are conjugate depths. They are not alternate depths. This means that they have the same specific momentum, but they do not have the same specific energy on either side of the hydraulic jump. There's an energy loss that occurs through the hydraulic jump, and so we wind up having a lower specific energy on the downstream side of the jump than we do on the upstream side. So how do we relate these two depths to each other? That is one thing we can do, and we can relate it by saying the depth after the hydraulic jump over the depth before the hydraulic jump is equal to 1/2 times the quantity square root 1 plus 8 times the Froude number before the transition squared, all of that minus 1. And just to kind of show and profile what's going on, here's our channel bottom, and here's our flow hydraulic jump, and this guy right here is y1, this one over here is y2, and we have a Froude number over here and a Froude number over here. Okay, we can also write this equation the other way and say that y1 over y2 is equal to 1/2 times the quantity square root 1 plus 8 Froude number after the transition squared minus 1. Okay, so we've just switched the numerator and the denominator here on the left hand side, and then replace the Froude number before the transition with the Froude number after the transition. Okay, so if we have the depth on one side of the hydraulic jump, and we have let's say we have the depth before the hydraulic jump and the Froude number before, we can predict what the depth would be after the jump, for example. So let's do an example problem similar to something we might do on homework or in a test or something like that. We have a rectangular channel. Its bottom slope is 0.0003. Its Manning's N for the material is 0.020. The width of the channel, which we also sometimes call B, is 10 meters. Our flow is 46.5 meters cubed per second. And our depth before the hydraulic jump, y sub I initial, is 0.5 meters. Question is, will a hydraulic jump occur? And if so, what is depth after the jump? So you could say, will a hydraulic jump occur, or can a hydraulic jump occur? What we're basically testing, do we have these conditions up here? Is the depth less than critical depth, which is less than normal depth? And we have our depth, 0.5 meters. So what's the critical depth? We have an equation for that in a rectangular channel that says the cubed root of the flow rate squared over G times the channel width squared. Cubed root 46.5 squared over 9.81 times 10 squared. And that equals 1.30. So we have an initial depth of 0.5 meters, our critical depth of 1.3 meters, so we are in supercritical flow. Now we need to calculate our normal depth and see if it's greater than the critical depth. Now in this case, we have a channel width of 10 meters and a depth of 0.5 meters. So we're going to use our assumption that the W is much greater than the depth. Okay, so we have an equation for calculating normal depth only in this condition. And here we have a width that's 20 times greater than a depth. So I'm going to make this assumption, and so then I can use that formula that says y sub n is equal to nq over w square root s0 to the 3/5. So that's 0.020 times 46.5 all over 10 square root 0.0003 to the 3/5. And we get 2.74 meters. Okay, if we didn't have this assumption, or if we weren't in a rectangular channel, we would have to iterate to find the normal depth. But we have this condition where now y is less than y sub c, which is less than y sub n. So hydraulic jump will occur. Now this is where it can get a little tricky. What can be happening on both the upstream and downstream side of the hydraulic jump is there could be gradually varied flow on either side. So when we look at this hydraulic jump picture up here that I drew, this depth right here is not necessarily the same exact depth everywhere before the hydraulic jump, and then over here the same exact depth everywhere over here. our equation here of y1 and y2, those y1 and y2s refer to just before the jump, just after the jump. Okay, just before and after the rapidly varied flow section, which is right here. We could have gradually varied flow then continuing on over here and continuing on upstream as well. So in this case, we had this y sub I of 0.5 meters. We weren't it wasn't specified whether that was just before the hydraulic jump or whether it was some area farther upstream that our current depth was at. But regardless, let's think right now, what would be the depth if we have the depth on one side? What would be the depth on the other side? So we could either make the assumption that the 0.5 meters, which was our yi, is this y sub 1 depth, and then calculate what y sub 2 would be, or we can make the assumption that this 2.74 meters is y sub 2, and then calculate what y sub 1 would be. Because when we go through the rapidly varied flow, the hydraulic jump, we're going to be going towards the normal depth. So we're going to make the assumption that the depth on the downstream side of the hydraulic jump is the normal depth, which is 2.74 meters. So then we can use our equations up here to calculate what would be the depth just on the upstream side. It could be y sub I, 0.5 meters, or it could be something else. So in order to use this equation right here, we need to calculate the Froude number on the downstream side. So Froude number 2 equals V over square root gy, which equals Q over A, or Wy, divided by square root gy. If I plug everything in there, I get 0.327. And now I can use my equation from up there. Y sub 1 over 2.74 meters equals 1/2 square root 1 plus 8 times 0.327 squared minus 1, and I get that y sub 1 is equal to 0.5 meters. So it happens to be the case that in this problem, 0.5 meters is the conjugate depth of the normal depth, 2.74 meters. It's not always going to be that way. It just so happened that that's the way this problem worked out. Okay, so the bottom line is we can predict the depth on one side of a hydraulic jump based on the depth and Froude number on the other side, and that a hydraulic jump will naturally occur when the depth is less than critical depth, which is less than the normal depth, because the flow is going to want to get to normal depth and will transition through the critical depth on its way from supercritical to subcritical. And that's about all we're going to do with hydraulic jumps.